Hey guys, today we're going to be doing the SN1 versus the SN2 reaction and a little bit of an overview on both of them. So to start, we're going to start with the SN1 reaction. It's a two-step nucleophilic substitution reaction. Second step comes from the carbocation forming compared to the SN2, which is just a straight one-step reaction. One of the big things for the SN1 reaction is the stability of the carbocation. So the SN1 will prefer a tertiary to a secondary, to a primary, to a methyl. Tertiary being the best, methyl being the worst. You can see a carbocation forming for each of these here. The reason why it prefers the tertiary over like a primary or methyl is because right here, this tertiary is able to hold the carbocation charge a lot easier due to the more surface area compared to the primary, which can't hold the charge and therefore is not as stable, where the tertiary is a lot more stable. Second is the big key feature of the SN1 is the carbocation intermediate, which we can see here and then through here. That's after the leaving group leaves. There's a positive formal charge that forms due to the lack of electron density there, and that's where a nucleophile will attack. That leads into my next point, which is the weak nucleophile, which is a big difference between the SN1 and the SN2. The SN1 prefers the weak nucleophile, so you'll see a lot of things like CH3OH, ETOH, and even water sometimes. These all are pronated and have no charge whatsoever, so they're a lot weaker compared to like some of the basic counterparts with like OH or CH3O, which are all strong nucleophiles. One of the other big features of the SN1 is the hydride and methyl shift. You can see two examples here, this being the hydride where this is a secondary carbocation here, but you can see that there's also a tertiary carbon here. So this hydrogen will go ahead and shift over and therefore moving this. Now we're going to go ahead and talk about the SN2 reaction. The SN2 reaction is a one-step nucleophilic substitution, so everything happens in one step. There is no carbocation formation or anything like that. The SN1 was a two-step reaction. So to start with, the SN2 will prefer a methyl substrate compared to a primary substrate compared to a secondary substrate compared to a tertiary substrate. The reason why it prefers the methyl and the primary the most is because since there is no carbocation formation, it's going to want to just get in there without any steric hindrance whatsoever. It wants it with no steric hindrance. The carbocation on the SN1, it was okay to be at a tertiary because the nucleophile could attack and there'd be the formation there. But since the SN2 is just happening all at once in one step, it wants it to be available so the nucleophile can come in, attack, lash itself on, and then the leaving group will expel itself. Second, obviously, as we were saying, the SN2 will have no carbocation intermediate. This will not occur. That's only an SN1 thing. The SN2 reaction also has no methyl or hydride shifts in it whatsoever. Since this all happens in one step, there is no chance for there to be a shift with a carbocation or anything like that. The SN2 also favors strong nucleophiles. So you'll see like CN, OCH3, OET, OH, BR, and iodide. They're all strong nucleophiles with that strong charge right there. These all are conjugate bases. And as you can see with things like BR and iodide, these are conjugate bases of strong acids. These are really good leaving groups here because they're able to stabilize themselves if they're by themselves in a solution, and they're able to hold that negative charge a lot easier than some not as strong leaving groups. So they're always used a lot, and they're the conjugate bases of very strong acids. And so next thing is with the SN2 is the inversion of stereochemistry. You'll see that instead of having a racemic mixture where you get both a wedge and a dash, the SN2 will get, so if you start with a wedge, you'll only get a dash. Or if you start with a dash, you'll only get a wedge. You can see here with the R to S or S to R. And then another big thing for the SN2 is that it favors polar aprotic solvents, like DMSO, DMF, and acetone. It's just likes dissolve likes. The aprotic solvents will prefer, most of these are relatively aprotic compared to the SN1, which had relatively protic nucleophiles and protic solvents, because likes will dissolve likes. And then also the SN2, here's a reaction diagram for an SN2 reaction. You can see that the reactants start, and then here's the rate determining step, and then since it only happens in one big step, there's only one transition state, and the products are less than the reactants. So that means that most SN2 reactions are mainly exothermic because they're releasing energy, and the products have less energy than the reactants. All right, so here's the SN1 versus SN2 comparison. How I like to always start these is when I'm given a problem like this, is I like to create a list. The list starts with, I always look at the substrate first. So you'll know if it's a tertiary substrate, generally it will be SN1. Obviously you need to look at all of these as a whole, but generally it'll be leaning towards SN1. And then if it's a methyl or a primary, generally it will be SN2. Second, you look at the nucleophile. If it's a strong nucleophile, it's most likely SN2. If it's a weak nucleophile, it's more leaning towards SN1. And then third, look at the solvent. If it's a protic solvent, it's more likely SN1, and if it's an aprotic solvent, it's more likely SN2. Again, you want to weigh all three of these together and see which way it's going to lean the most. And so I like to weigh it like that. So we're going to go ahead and do a quick two problems. Here's one of them. So this OCH3 is going to react with Cl. So first let's look at the substrate. Since this is a chair conformation, it's a cyclohexane, we know that this is a secondary substrate. So okay, well that doesn't tell us either. That doesn't tell us that it's an SN1 or an SN2 because it's right in the middle. So we can go ahead and just put a check mark for both of these here. Since we know it's secondary, and I'll write secondary right there. And so, okay, well, we can see that this is a strong nucleophile because of the charge, and it's very nimble and is able to come around either way. So this is a strong nucleophile, OCH3 is. So we can go ahead and check mark that. And then the solvent is aprotic. DMF is a very common aprotic solvent. So this is most likely leaning towards an SN2. So what we can do is we'll go ahead and have this attack from the rear, come around, attack, and then since this is an axial position, and there's the inversion stereochemistry, the final product of the OCH3 is going to be in the equatorial position. Think of the wedge and the dash. So it's the same thing. It's the R to S inversion of stereochemistry, and you'll have the chlorine sitting in the solution. We'll go into the second problem now. All right, so here's our final example. We can see here that we're going to start with, we're going to look at the substrate. So here we have the substrate. This is a secondary substrate. But notice there is the possibility of a hydride shift here because this is a tertiary carbon that is connected to the secondary carbocation carbon. So okay, we'll go ahead and we'll do 2/3. So this could, right now, this could still go either way with the possibility of it being SN1. So let's go ahead and look at the nucleophile. All right, well, H2O is a relatively weak nucleophile, so that's leaning more towards SN1, and then the CH3OH is a protic solvent. A protic solvent is SN1, so that's what the SN1 favors. So we're going to go ahead and do SN1. So as we know with the SN1 reaction, the first step in every SN1 reaction is the leaving group will leave with the formation of the carbocation. You can see here's the carbocation. Since we're on a secondary and the tertiary carbon is right there, the hydrogen is going to go ahead and move over here to accommodate the carbocation, therefore moving the carbocation over here to the tertiary where it's able to be more stabilized. The nucleophile will then attack the carbocation, or the carbon with the carbocation coming from here. It can also attack from here. It can attack the carbon either way there. Then we get the pronated water molecule here on the substrate, and this has a plus, so we need another water molecule to come in here and deprotonate this water molecule. This water molecule is going to take the hydrogen, and then the electrons that are bonded here are going to fall back on the oxygen, getting rid of the plus charge. And then you're going to get a racemic mixture here of a wedge and a dash of the OH, because again, the water can come from the front or from the back, and that's what you get that from. And we looked at our list, and it was all good, and this all lines up correctly. So I hope you all learned something from my lesson, and thank you.